I think many of us are familiar with the notion that the language of digital electronics consists of ones and zeros. But here's the thing. There isn't actually ones or zeros running through the circuits in the chips. There's actually the whole spectrum of analog electricity going through those chips. All we do is we say, well, if the voltage is below a certain number, we'll call that a zero. And if it's above a certain number, we'll call that a 1. But indeed, at a physical level, digital electronics is truly analog. And that fact was overlooked by me in our last video. So in episode 14, we created a digital logic circuit. And it started, well, after we created the circuit, it ran very well. But I started to notice that as I started to continue to play with the circuit, it started exhibiting some very interesting challenges. And those challenges, after quite a bit of discovery and research, I found out have to do with this fact that zeros and ones are truly analog. We had a situation where there was a transition occurring from 0 to 1, and that transition wasn't timed very well. And as a result, the voltage landed in between a 0 and 1, and what that manifested in was errors in the circuit. So I learned that we had to put some delay into the circuit. Now, it's not easy to delay electrons flowing through a circuit, but what we can do is, because digital electronics is actually analog, we can control the time it takes for a 0 to turn into a 1. Or vice versa, a 1 turn into a 0. And it was that fact that I leveraged in order to solve our problem. So stick around, and we'll see how capacitors can introduce delay into electronic digital circuits. So here's a picture of a bunch of capacitors that I found on Wikipedia. Capacitors are varied, to say the least. There's all sorts of them. Big ones, small ones, oddly shaped ones, cylindrical ones, flat ones, tiny ones. They're all over the place. But all of them, regardless as to what they look like, do the exact same thing. There's always two terminals to a capacitor. And just very simply, here's the way they behave. So imagine for a second that we were pouring current or charge into one terminal of that capacitor. As that charge continues to go into that capacitor, the voltage across the two terminals increases, and it will continue to increase until the voltage meets that or equals that of the supply. This phenomenon is really cool because there's two things that we can do here. We can control the rate at which we pour charges into that capacitor, and we can control that using a resistor. We put a resistor in series with that capacitor, and what that's going to do is it's going to allow us to either slow down with a big resistor or speed up with a little resistor the speed at which those charges go into that capacitor. The other thing that we can do is we can change the size of that capacitor. A bigger capacitor will take longer to fill than a smaller one, and so therefore the time it takes to go from 0 to full or from full to 0 can be controlled. And it's going to be this phenomenon that we're going to leverage to solve our problem. Take a look at the circuit that we have here. Now, first off, I'm going to apologize. This is a disaster. We've taken about maybe 14 episodes to get to where we are today. And over the past 14 episodes, we've been evolving and changing and tweaking and doing all sorts of stuff to our circuit. And as a result, it looks like this bowl of spaghetti on the table right now. So I promise I will clean it up. Not today. In a future episode, I'm going to make this a lot cleaner. But for now, let me show you what's happening here. And through that description, I'm going to identify the problem that we saw. So on the left, we see this little green blinking LED. This green blinking LED is being generated by that chip over there. And that's basically the clock pulse. Up and down, up and down, up and down. On the right side, we have two chips over here. And those two chips are counters. Binary counters. We have two buttons over here as well, which are kind of tough to see behind this mess of wires. We have a down button and an up button. The down button obviously makes the counters go down. The up button makes the counters go up. We have five LEDs here, the blue LEDs, and those 5 LEDs basically tell us the intensity level of the LEDs, the high-powered LEDs, where this is actually going to. And you can see those high-powered LEDs over here. So basically, these 5 channels give us 32 intensities for these LEDs. And as I increase the intensity by pushing this up button, you can see the intensity of the LEDs increase. And if I decrease it by pushing the down button, you see them decrease. You probably also noticed a red LED here that indicates we're going down, and another red LED here that indicates we're going up. There's some additional logic in here that those two chips in between are managing, and that logic is as follows. When we increase the LEDs to the maximum, and in this case, those are 32 levels up, so number 31, you see all those 5 LEDs lit up, it will not go any higher. And if I push the other button down, it goes all the way to 0, and it stops at 0. It will not go any lower. That's what these two chips over here are doing, that logic. Now, what we discovered, that although the circuit works on the surface, occasionally, if I keep pressing those buttons, what happens, at least what I found was, on the upside, the downside worked perfectly fine, but on the upside, every now and then, the counter allowed itself to go past 31 and go into 32 and beyond. And I said, well, that can't happen because we put the logic in place to prevent it from doing that. Another problem I saw was that sometimes when I released the up button at the maximum count, even though the count was supposed to be 31, sometimes it dropped back down to 30. Even though I didn't push the down button at all, the counter decreased. So that's another peculiarity that I looked into. Now, why was this happening? We had to dig in a little deeper to figure that one out. So let's dig in. Here's the circuit schematic of the circuit you just saw. We had those two buttons over here, down and up. We have our two counters over here. These are the counters that count from 0 to 31. And we also have the logic in here, which prevents the counters from going below 0 and above 31. Okay, the magic ingredient in here, because I don't want to spend all this time explaining what's happening. If you're interested as how the circuit works, go back and look at episode 14. I'll put the link in the description so you can go take a look. But the magic ingredient here is this little piece right over here. This is an AND gate. And the way this AND gate works, the way I can describe it without getting too detailed is almost like, think of a nightclub. Now this particular nightclub has 3 bouncers. Let's call them bouncer X, bouncer Y, and bouncer Z. For our American friends, bouncer Z. This clock input is kind of like that guest that wants to get in. So it's constantly trying to get past those bouncers and into the counters over here. But there's 3 bouncers preventing that guest from getting in. Let's look at bouncer X. So bouncer X is the one at the bottom over here. And bouncer X is going to be in position blocking the door until somebody pushes either the up or the down button. When one of those buttons are pressed, bouncer X will go take a break. Bouncer Y is this input over here, and bouncer Y is always going to be blocking the door if the count is at its maximum, meaning the count is at 31, and the up button is pressed, meaning we're trying to go up. In that situation, the bouncer is going to be blocking the door. If the up button is not pressed, or we're not at the maximum count, that bouncer is off on a break. And let's look at bouncer number Z, or bouncer Z. Bouncer Z. This bouncer is only going to jump into action when the counters are counting down and the counters have reached 0. So at that point, this bouncer is going to get up and block the door. Said, nobody else in. We're at 0. We can't go any further. Now, for this analysis, we never saw a problem when we were counting down. So let's assume that bouncer Z is having his Z's. Bouncer Z or Z is going to be sleeping. We are not concerned with bouncer Z or Z for this particular analysis. We're only considering bouncer X and bouncer Y. What ended up happening was when I pushed the up button and the counter got right to the top, okay, so it's at 31. Remember, bouncer Y is going to be blocking the door now, saying, can't get in. Bouncer X is letting people in because, well, I shouldn't say letting people in. Bouncer X is not blocking the door because the button is pushed. So bouncer X is standing back, bouncer Y is blocking the door. As soon as I release the up button, bouncer X jumps into action and blocks the door, and bouncer Y goes away at that very same moment. But what was happening was there was a time in that transitionary period, not all the time, but sometimes, where neither bouncer was blocking the door, and the clock was able to squeak through. The other situation, or the other phenomenon that I saw, slightly different, nearly the same, was when bouncer X is blocking the door, bouncer Y was not. And when I released the up button, as soon as I did that, let me rephrase. Bouncer X is not blocking the door. This is the second scenario. Bouncer X is sitting back, bouncer Y was blocking the door. As soon as I release the up button, bouncer Y then goes away and bouncer X jumps into action. So there's another transitionary period where they switch roles again. Now, yes, there is a time when they're both not looking at the door, but in this situation it was a little bit different, because what happens is as soon as bouncer X jumps into action because the button is released, this up button is also connected to the direction. And what would happen is the direction would fall to 0 because of that line over here. And when it falls to 0, that means the counters are counting down. And also, there was a time when both bouncers are not looking at the door, and so the clock snuck through. And so that's why the count ended up going down 1. So both of these scenarios are occurring because of our timing. It's not set up to ensure that there is never a time when the door is not blocked. So now that we know what we're trying to achieve, how can we put the circuitry in to make that happen? Well, think about this in terms of the points that we need to really focus in on. So we need to focus in on this point over here, because this point, let's call it point X. In other words, for bouncer X. But bouncer Y is controlled from this point over here. So can you imagine what's happening here is that the signals, as soon as we push this down, the signals over here are going to be rising. So there's a situation where we have to look at when the signals are rising, and that is a transition from 0 to 1. And there's also a situation where when we release that button, the signals drop. So there's a transition from 1 to 0. And without boring you and going on to the details, I figured out what the comparison needs to be between X and Y. And this is basically what we're trying to achieve here. If you forget the bouncers for a second and look at just the positions, what we want to achieve is when the signals rise, point Y needs to rise faster than point X. And when the signals drop, point X needs to drop faster than point Y. You get that? That is exactly what we're after. And how are we going to induce that kind of timing? With capacitors, of course. So we have to put some capacitors into these points, point X and point Y, so we can control the timings independently. Now you may be thinking, well, actually, point X and Y are really the same point in this circuit. And you're absolutely right. They are the same point in the circuit, which tells us that we're going to have to change the circuit considerably in order to put those capacitors in here. Okay, so let's get into how we're actually going to change these circuits. Remember, a capacitor functions through a resistor. Remember the earlier explanation. In order to charge the capacitor, we pour charges in through a resistor and into the capacitor. And to discharge that capacitor, the charge runs through a resistor and out into ground. Let's consider point X first. So here's point X over here. We've put our CX, which is our capacitor, into the circuit, and we also have 2 resistors in place, and there's our up switch. I've called this RXR, which is the rising resistor for point X, and this is RXF, which is the falling resistor for point X. So in other words, this capacitor, when it's getting charged, it's going to charge through this resistor, and when it's getting discharged, it's going to discharge through this resistor. And based on the different sizes of those resistors, we can control the rate at which this happens. Now, what we know based on our earlier, not assumption, but our statement, is that point X needs to fall fast and rise slow. Right? That's what we know. So that means that the speed of charges flowing this way needs to be quick, and the speed of charges flowing this way needs to be slow. The capacitor doesn't change, but the resistors can. So that means our XR, or this resistor over here, has to be big, and this resistor over here has to be small. Now, there's a problem with our circuit. Consider the situation when up is pressed. When up is pressed, this is a big resistor, and this is a small resistor. But think about what the actual voltage will be at point X. If a big resistor is here and a small resistor is here, this behaves as a voltage divider. And even though we've pushed the up button, the actual voltage at point X is going to be very small indeed. With this scenario, we're never going to be able to get a high voltage or a high level on point X. We can never get the 1. It's always going to be a 0, regardless as to whether or not the button is pressed. This is not going to work. We need to change the configuration of the switch. Here's an alternative configuration of the switch. Rather than using the switch to charge the circuit or charge the capacitor, I can use the switch to discharge the capacitor. Now think about this. If I use the switch to discharge the capacitor, let's say the switch is not pressed. If it's not pressed, then the charging path is going through RXR to charge our capacitor. When I press the switch, the discharging path is going through RXF, which is exactly what we want. And even though this is a lot bigger than this, when the button is not pressed, this path doesn't exist, and so the voltage at point X will always be 12, or whatever the supply voltage is. In other words, we're going to get a good solid 1. When I push the switch, that means because this is going to be because this resistor is big and this one is small, the value at point X, or the voltage at point X, is going to be very low indeed, even when that button is pressed. So we're going to get a nice, good 0. So this will work. The problem, though, with this is that the switch is now reversed, right? What I want is I want the action to occur when I push the switch, not when I release the switch. And right now it's configured so that the action is occurring when I release the switch. This is a bit backwards, right? It's not going to be intuitive for the user. So we have to put an inverter into this mix as well. Well, we can do that. We have MOSFETs for that purpose. Here's the same circuit, but with the MOSFET added in. And the MOSFET in here does one thing. It inverts the signal. So imagine when this button is pressed. When this is pressed, the point over here is actually going to be 0. It's going to be grounded, which means that this MOSFET is disengaged. If this MOSFET is disengaged, when I push this button, the charge path is lit. When I release the button, that engages the MOSFET and the discharge path is lit. So this MOSFET allows the button to take action when we press it and discharge when we release it. This works very well. Slight adjustment is needed though. This is a physical switch, and generally we want to keep the current flowing through switches at a bare minimum because we're always trying to, there's contacts rubbing and disconnecting, connecting and disconnecting. So there could be sparking going on here if the current is too high. And right now we don't have anything to limit the current going through this switch. That's very bad indeed. In fact, without anything in here, that's a short circuit, so not good at all. So I put a 100 kilo ohm resistor over here and a 10 kilo ohm resistor over here. That's going to make sure that the current going through that switch is extremely small, but it's also going to make sure that when this is pressed, this node over here goes close to 0, and when it's released, it's going to be a nice solid 1. This will give us exactly what we need to make sure that that capacitor charges slowly when I push the button and discharges rapidly when I release the button. I think our X is nearly there. Let's look at Y. So Y is being driven by the same switch. Don't forget, the same button is driving it, and I need to invert the signal. So if I try to do something like this, then I can invert that signal, but here's the problem. With position X, we needed a rise time that's long and a fall time that's short. With position Y, that is not the case at all. In fact, with position Y, the rise and the fall time are the same. Remember the sentence that we came up with, so the pair of sentences. Position X needs to fall faster than Y, and position Y needs to rise faster than X. So all we've done so far is we've made X rise slow and fall fast, which is good. But the Y needs to rise faster than X, but and also fall slower than Y, or slower than X. So what that means is the Y is kind of medium. It's rising and falling at the same rate. So so basically the rising resistor and the falling resistor need to be the same, or roughly the same, in order to get this transition timing the way we want it to do. Okay, so I can put two resistors in place here. So imagine what happens when I close that switch. Then if I close the switch, this point over here goes to 0, which disengages the MOSFET, and it allows the charging resistor to take into action. When I release the switch, the discharging resistor goes into action. So far so good. But if these two resistors are the same value, then when the switch is pressed, this point over here can never exceed half of the supply voltage. So if our supply voltage is 12, this will never go above 6, which means, again, I'll never get the 1 that I need over here. This is going to cause a problem. So there is something else that we can do to resolve this situation. Here's an alternative setup that will get us what we want. So what I've done is, rather than using a single MOSFET, I've used two, a complementary pair. This is the N-type MOSFET that they're all familiar with, but over here is a slightly different beast. This is a P-type MOSFET, and functionally it's kind of like the opposite of an N-type. And when you put it into this configuration, what ends up happening is when I press this button, then just like before, this position is going to be 0, and this MOSFET is going to be disengaged. So the discharging path is now removed. But the P-type MOSFET works the opposite. So it's actually going to be engaged, which means we're going to have a charging path through this resistor over here to that capacitor. Now, when I release this switch, these MOSFETs are going to switch jobs, and the discharging path is going to be activated and the charging path is going to be deactivated. So the capacitor is going to discharge through the same resistor. So this configuration allows us to use one resistor as a charge and discharge resistor, and it also ensures that the point at Y will get either a 0 or a 1, and it's going to be a nice solid 0 or 1. Now, how do we build this CMOS, or this balanced circuit? Oh, I slipped. How do we build this balanced MOSFET arrangement? Well, I told you before that these are tied together, so they're actually complementary. And the C in complementary stands for CMOS. And so, of course, that's what I slipped earlier. I mentioned it. But this is a very common arrangement. In fact, it's so common, it's available in nearly every IC that we see today. And so I could go out and buy a P-type MOSFET and match them up this way, but they're not going to be very well balanced. You actually need to put them right onto the IC or put them onto a chip so that they balance really well. And like I said, they're available everywhere. Take a look at this. This, of course, is our circuit, right? I've used a different visual of the circuit. Instead of using the gates that we had previously, I've actually put in the chips that we used in our circuit for episode 14. And the chips that we used are 4012 chips. These were for the NAND gates. So this enabled our logic. But remember, when we use these gates, each and every one of those chips has two gates on it, two 4-input NANDs. So this particular chip, we ended up using both of those inputs, or both of those gates. But this chip, we only used one, which left the other one available for us. And these chips happen to be CMOS chips. So the output of every CMOS chip looks just like that arrangement you saw earlier, which means I could use this NAND gate as a CMOS inverter, and that will help us accomplish exactly what we need to do. So that's what I did. Here's our Y circuit using the 4012 chip as a CMOS inverter. So when this button is pressed, then this point over here is going to be 0, right? Because it's going to be nearly grounded. It's going to be low, and that goes into the NAND gate. And because if any input in the NAND gate is low, then the opposite is going to be true for the output. So we're actually going to get a nice high over here whenever we push that button. When we release that button, this becomes a high. And since all the others are automatically tied to high, then the output over here is going to fall to 0, or going to fall to a low, and it's going to give us a low over here. And this path is also going to serve as that CMOS charging and discharging path. So that means that this capacitor will be charged through RY and discharged through RY. So I think that's going to allow us to control point Y as well. Let's put it all together into our new circuit. So here we have the circuit with the X arrangement and also the Y arrangement. So this configuration will work for us. Now remember, all we need to do, actually I shouldn't say remember, all we need to do now, our next step, is to figure out what the values of RXF, RXR, and RY are. We know what the values of CX and CY is. Well, it's not that we know them. I decided to use this. This is our 0.1 microfarad capacitor, I got a couple of these, and I'd like to use these for Cx and Cy. So all that remains to do is figure out the values of those. Now, if you think about our statement that we came up with, the statement, I'll repeat it again for clarity? I don't know. I'll repeat it again. The statement is y must rise faster than x, and x must fall faster than y. So what that means is, of these three resistors, Rxf needs to be small, Ry needs to be medium, and Rxr needs to be large. All right, that's pretty straightforward. But how small, how medium, and how large? For that, we're going to have to roll up our sleeves a little bit more to get detailed. I have two charts over here. I have a fall chart and a rise chart. These charts are going to help us determine the size of those resistors. Now, what we know is that Rxf has to be the smallest resistor possible, and Rxr has to be the biggest resistor possible. So the question is, how small and how big? Well, we can start from either end, but I chose to start from the small end, and here's why. Notice the discharge path of this X capacitor. The discharge path goes through Rxf, which is what we want, and it's also going through this MOSFET. Okay, now this is important because if it's going through the MOSFET, we have a limit to how much current we can push through that MOSFET, and that's going to help us figure out what the fastest possible discharge rate can be. So this MOSFET we happen to be using is the same MOSFET we've been using all along. It's the BS270 MOSFET, and if you look at the data sheet, the BS270 MOSFET says that it can support a maximum of 400 milliamps. Okay, so 400 milliamps is our limit. So if I go back to our charts, let's take a look at some of our numbers that we've put in here. The first item that I've identified is the capacitor for X. We've chosen it at 0.1 microfarads. We already know that. The maximum current that we can do for IXF, which is the falling current, is 0.4 amps, which is based on the BS270 limitation. So using Ohm's law, we figured out that the resistor, RXF, needs to be greater than 30 ohms. Okay. Well, I don't actually have a 30 ohm resistor, and it does say it needs to be greater than to protect the equipment. So the next reasonable step up that I have lying around actually happens to be a 100 ohm resistor. So that's the one that I'm going to use. Now, if I put a 100 ohm resistor in, we know that the capacitor we're using is 0.1 microfarads. With those two values, we can actually calculate the curve of the discharge. So if we start at 12 and I discharge that capacitor, the capacitor discharges really, really, really quickly, and then it slows down the discharging. But eventually it approaches zero as time continues. And so we know that capacitor X is the one we want to discharge quickly. So I'm going to label this as a discharge curve for X. We also know that the discharge curve for Y has to be slower than that. So let me draw another one that is going to be slower than this. It's the same shape, but it's going to take a much longer time to discharge. There's something else that's already put onto these charts. I want to explain what that is. There's these two horizontal lines over here. Now remember earlier when we first started this video, I was talking about how the physics behind digital electronics is truly analog. But what we do is we categorize those analog values as either a 0 or a 1. And so, well, what is the value where... So let me repeat. So if we take the range of values that we could possibly have, our supply voltage is 12. So within that 12 volt supply voltage, there's a certain number upon which anything below that number was considered a 0 or a low, and anything above that number is considered a 1, a logic 1, or a high. Well, what are those thresholds? The kind of chips that we're dealing with here are CMOS chips. And CMOS is a very well documented technology, and within that technology, we know what those values are. CMOS technology says that the lower 30% of our supply range is considered a 0 or a low. The upper 30% of our supply range is considered a 1 or a high. So for a 12 volt supply range, that works out to 3.6 volts, anything below that is a low, and 8.4 volts, anything above that is a high. So you may be wondering, well, what about the area in between? And that is the problem, or that is the source of the problem that we were experiencing. See, right now I've drawn two different curves here, and these two curves are timed curves. I've said that X is going to fall fast and Y is going to fall slowly, and that's why they look the way they do. But right now, our circuit isn't like this. In our circuit, the X and Y points are falling at exactly the same rate. And so this area in between, I'm going to call this the danger zone. We do not want to linger in this zone, because in this zone, the electronics can't tell whether it's a 0 or a 1. And that's why the answer is unknown. So what was happening in the circuit right now is the X bouncer and the Y bouncer were changing roles within the danger zone. And that was the problem. What we need to do is we need to make sure that the bouncer X gets through the danger zone and enters the 0 zone before bouncer Y leaves the 1 zone and enters the danger zone. That way we can ensure that the door is always going to be looked after and both bouncers will not be in the danger zone at once. So this point right over here is important, and this point right over here is important. So these 2 points are our critical times where we need to be able to monitor in order to get our results. So based on these values, this capacitance of 0.1 microfarads and an RXF of 100 ohms, we can actually calculate this. We can calculate that time, or what that time is for that particular curve. And the equation to calculate that, complicated. I'm not going to go into the reasons as to why it is, but there it is. Okay, so it's based on the resistance, the capacitance, and this monstrosity over here, which is basically the ratio of the total supply voltage. And so that's how that equation turned into this. So it's RXF times the capacitance X ln 0.3, and 0.3 is the 30% mark. So that's what we're interested in. And if I work out the values, it works out to 12 microseconds. So this point right here is the 12 microsecond time. So bouncer X is going to get to the 0 zone in 12 microseconds after the button is pressed. Now, this capacitor is not exactly 0.1. There's always going to be manufacturing defects and changes and stuff like that. And the resistor that we're using, the RXY resistor or the RXF resistor, 100 ohms, is never going to be exactly 100 ohms. There's error built into it. So we know that this capacitor has an error of approximately 15 to 20%, I think. And the capacitor or the resistor also has an error, could be between 1 to 5%. So let's just say the error is as much as 25%. And so what that means is, although I calculated this time to be 12 microseconds, it could be as much as 15 microseconds, given the error in the manufacturing of these components. Okay, so this is going to be important for us to know, because I need to figure out, or we need to figure out, what that time is. And technically, as long as this time occurs after 12 microseconds, we're in the clear. But like I just discussed, there's error. And so we got to give it some buffer just to make sure that we can surpass the amount of error that might be in our manufacturing. So the calculations to figure out the error and all of that sort of stuff, it exists, but I didn't really want to get into it. Besides, I'm not going to be picking and choosing very tight precision parts here. I'm basically using the parts that I have lying around. So because of that limitation, I decided, you know what? I'm just going to pick the next resistor that I had in my box. The next resistor that I had in my box happened to be a 510 ohm resistor. So I chose a 510 ohm resistor for RY. I figured let's try it. Now, putting it into the equations, the same equations that we're using here, this time you see a 0.7 here because we're trying to figure out the time at this point in the chart, not over here. So that's 70%. So once I did that, I figured out that it was 18 microseconds. Okay. That's bigger than 12, and it's also bigger than 15, but there is some error built into this as well. And the error, I figured out based on the components, it means that the value could be as low as 13.5 microseconds, which is lower than 15. So I don't want to do this. It's cutting it far too close. So I went the next step up and I said, well, let's try 1 kilo ohm resistance. And if I do a 1 kilo ohm resistor for RY, it turned out to be 36 microseconds. And with 36 microseconds, even with the error, we got down to 27 microseconds, which is plenty above 15 microseconds. So I was very happy with that. So far, so good. We're getting close. We've picked our we've picked our RY at 1 kilo ohm. We also have our RXF at 100 ohms. The next step is to solve for RXR, the rising situation. So here's the rising chart. What I'm going to do is, because we have the same resistor in the Y capacitor for the discharge and charge, it's the same resistor, I'm just going to draw that in. But the scale is going to be different here, okay? Because we have to, well, you'll see. There is my rise curve for Y. There's my rise curve for X. So what we need to do in this situation, remember, we have to make sure that we're outside of that danger zone. So what we did was, I figured that if we're using the same resistor we were before, well, we are, it's going to be Ry is 1 kilo ohm. If I put Ry in here and do the same calculation, I found out that the time for the rise on the Y capacitor is 120 microseconds. Okay, so what that means is, when we're going up, Y will reach this point at 120 microseconds. And so what we also need to do is we need to make sure, well, we need to figure out what this point is. And we got to do the same thing we did over here, is worry about that buffer using the error. So rather than going through the whole rigmarole again, everything kind of scales up nicely. So rather than just trying to figure out what I needed to do, I chose a 10 kilo ohm resistor to use for RXR. And when I did the math, the 10 kilo ohm resistor resulted in a time of 360 microseconds. So that means this point occurs at 360, which is well above any sort of error that could be in our system. So that means we've chosen our values. As a summary, here are the values that we've chosen. RXF, the discharge resistor for the X capacitor, is 100 ohms. RXR, the charging resistance for the X capacitor, is 10 kilo ohms. RXY, the discharge and the charging resistor for the Y capacitor, is 1 kilo ohm. And here they are in the circuit. I told you that was a little hairy, so I'm glad you're still with me, but we had to go through all that work to figure out what those values were. It was a little painful, but we're nearly done. So I've put the values in: 100, 10 kilo ohm, and there's our 1 kilo ohm. We also put in the 0.1 microfarad capacitors over here, and we still have the remaining circuit as we did before. I did add a little bit more here because I wanted to move a little bit further than we did last time. Well, not last time, but a little bit further, so that we can talk about another challenge that I discovered. I put in the down button here too, just for completeness. And when the down button is here, you'll notice that it's going to these diodes. Now, these diodes were in the first diagram as well. They were in a different position. They weren't actually oriented like this. But the purpose of these diodes is an OR gate. Remember, we had that OR gate right in the beginning of our original circuit. Well, we still need that OR gate, so that's why these diodes are here. And if you remember from episode 14, we chose to use the light up diodes. The reason we did that is because I wanted to see when we push the up button and when we push the down button. So that's why we use the LEDs. All right, so it worked in the last circuit, but in this circuit it didn't. And here's why. Because of the sizes of these resistors, notice this is a 10 kilo ohm resistor. In the original schematic, this resistor down here was also a 10 kilo ohm resistor. And so that creates a voltage divider, right, when the button is pressed. And that voltage divider means that this point right here at the end of the OR gate will never exceed 6 volts. Of course, that's going to be a problem. We need this to actually register a 0 or a 1 depending on what's happening here. So I had to change this resistor to 100 kilo ohms. And when I change that resistor to 100 kilo ohms, that means we're going to get a 0 and a 1 over here. So that part works well. But now the current is so small, these LEDs will never light up. So I couldn't use the light up kind of LEDs in this situation. So I had to convert these to regular old-fashioned diodes in order to get the circuit to work the way I wanted to. I also added in another resistor over here just to make sure that this diode is discharged when we release the down button. But I still want to see the light. I still want to see when I'm pushing up or pushing down. I just had to wire them in separately. So to put the LEDs in, it wasn't all that complicated. The down was actually quite easy. All I did is I added in our light up LED right over here with basically a resistor of any size I could choose in order to get us the nice good brightness over here. The up was a little bit more complicated because remember, our up is inverted, so I needed to use another MOSFET to make sure that the light turns on when you push the button. And that MOSFET you can see over here. So I've tied it into the output of our CMOS output over here, and that MOSFET basically turns on the LED whenever the button is pressed, and when the button is released, it turns off the LED. And of course, we can use a resistor of any value over here in order to get a good brightness. In fact, I think in our circuit, I used a 1 kilo ohm resistor, which gives us a nice bright LED whenever we either push the down or the up button. Okay, so that is how we got to this circuit, and the rest of it is pretty much the same with one tiny little change, because I was on a roll of putting 100 kilo ohm resistors in here, and I'm also on a roll of using 0.1 microfarad capacitors. In the last video, this capacitor was a 0.01 microfarad, and we had a 10 kilo ohm resistor. So I just swapped it with a 0.1 microfarad, and in order to keep the timing the same, I had to up this as well to no, actually, it's the other way around, isn't it? Yeah, it is the other way around. Anyways, when I changed this to a 0.1 microfarad capacitor, and then I changed this to a 100 kilo ohm resistor, which basically extends the time of this reset. Anyways, I don't want to get into any more detail there because I think I've talked a lot on this episode, so we're pretty much going to wrap it up. But that is how we got to the final circuit where we are right now. And here's the result. This incredibly tightly packed breadboard with all the circuitry that we talked about earlier. I'm very sorry I couldn't build it here on this video. A, this is already a very long video, and B, truth is, I built it while I was testing and I really didn't want to dismantle it. Side note, I don't think I've ever used every single available slot on a breadboard until today. I think I've used every slot on this breadboard. There is no free circuits. That's a pretty cool achievement. And it actually all fits and it works. Anyways, this is our circuit. And I have not yet been able to create that same malfunction that we saw in the previous version, or basically which led us to this video. I have not been able to recreate that challenge, and I think we're in a good spot. So I hope you enjoyed today's extremely long, extremely detailed, and very deep video about how we can inject, or how we can use capacitors to inject some delay into a digital electronic circuits.